Hello. Hello. Hello, Josephine. All right. And good afternoon, Eric. All right. Good after. All right. We're going now. Okay. Good afternoon, Maria. All right. All right. Good afternoon, Eric. Good afternoon, Paulina. Good afternoon, Jenna. Good afternoon, Katie. Good afternoon, Alexis. Good afternoon, Logan. Good afternoon, Shirley. Good afternoon, Claudia. Afternoon, Maria. Good afternoon, Victoria. Everybody said good afternoon. That's awesome. Okay. And Josephine, for sure. I think we said that, but she didn't. Okay. And Eric and Alexis and Jada and Paulina. And okay. I think, I don't know if there, good afternoon, Emily. All right. All right. That is awesome. Sorry. Good afternoon, Victoria. Excellent. Okay, we're all here. We're all here. Did I say everybody? And did I say? I think I said everybody. Okay, and Shirley. Okay, let's get to homework 7. Um. Okay, I'm gonna go straight to homework 7. Homework 7 starts. So homework 7. Well, I'll just say this. It's all about. Oh, sorry. Yes, Josephine. Yes, I'm sorry.
Are we gonna be going over the practice test together?
Well, we're not going to explicitly walk through the whole thing. There will be at least a day where you can ask questions about it and I'll answer them. Wait, which period? There will be a period where we do that. We're not going to walk through the whole thing, but you definitely can ask questions about it. And I haven't posted it yet. I know there is something there that you can look at now, but I'm going to update it for this semester. Hopefully by tomorrow night. There might be, I can't promise this, but I have to talk to you. You might be you might be addressing it directly in a lab period. It depends if we have. So I still have to talk to Professor Walters about that. But there's definitely going to be a day where you can ask questions about it and I'll answer. So yeah, but
Okay.
yeah, okay. And I'm losing all track of time and when, but yeah, the practice. I guess that day would be either this coming Monday or Wednesday. I can't, but certainly I'll say this too, right? Because if it's posted by tomorrow night, certainly if you come in Monday, I will. I mean, if you come in with any questions about it Monday, I will answer them Monday. Like I'm not going to wait.
Okay.
Yeah, okay.
Will there be like an answer key or something that's
Well,
uploaded maybe?
okay. So the thing about that is I will give some solutions, and I'll answer some. I will give some solutions and post some solutions, and you may get some solutions in lab. It is a very fair question, of course, and you'll get some solutions in lab. But here's how it works with solutions: anything that we give you a solution for. So, I'm just letting people in. Since the actual test will be very, 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 very similar to the practice, what we do is if we get anything that we give you a solution for, then we'll change, then you can expect that we would change it slightly for the real thing, like change the numbers or change details. So it's not exactly the same question, but anything that we don't give you solutions for, the sort of compromise or the deal or the flip side of that is anything on the practice exam that we don't give you solutions for. That's our way of saying, okay, this thing, if we don't give you solutions for problem 2, then problem 2 will appear on the actual exam exactly as is. So the things that we don't give you solutions for, what you can just basically consider is that we've given you an extra week sneak peek to prepare in advance and know exactly what it's going to be without surprises. And you can work with other people and all of that. So some things we don't give you solutions for because we're basically saying, like, here's a problem. You have a week to figure it out before you even get the exam. Then you get the exam, you'll have 5 more days to figure it out. So that's like the deal. I mean, if we don't give you solutions for something, then at least you know that's the exact problem. So now do whatever you can, like consider it a research project or whatever. Go off with your friends and do whatever you can to just get answers to it because you have the time. But anything that we do to give you solutions for will change details slightly. Does that make sense? Okay, but very good question. Very good. But yes, I mean, again, just to answer the first part of what Josephine asked also, because there's so many classes this semester and they're all having exams at the same time, which is what I always try to avoid, but I always fail to avoid. So I'm getting my dates confused in my mind. But right, if we're posting the practice exam tomorrow night, right, then that means certainly, I'm saying this to everybody, not just Josephine, certainly anybody who comes in, I mean, on Monday, next Monday class, with any questions at all about the practice exam, yes, I'll definitely answer them. And I'll add this one last thing also to that. And I'm not saying I won't also on Wednesday, but I'm saying, yeah, like that's the purpose of the practice exam. The more you deal with it, the more I'll respond to what you dealt with. But the way to deal with it and the way to take advantage of what Josephine is saying is the more people on Monday come in, the more specific each one of your questions is, then the more questions I can answer and the more of the practice exam I can like address. In other words, and I'm saying this again to everybody, like it's a good question from Josephine, but saying to everybody, if anybody comes in Monday and just says, can you go over problem 2 on the practice exam? I may or may not do that. I'm not saying I wouldn't do that, but just saying, can you go over problem 2? 2 things. One, you all know me. Once I start actually walking through it, which I might, well, then I'm going to like take 35 minutes and walk through the whole thing or something. And it'll be very difficult to get to any other problem in the exam for anybody else who wanted to see problem 3 or something like that. And also, to be really super honest about it, if anybody just raises their hand on Monday and just says, can you do problem 2? That doesn't really indicate that anybody's like try. And I'm saying this in advance, so it's not a criticism. No one's done this yet. But if someone just raises their hand and says, do problem 2, that doesn't really give, anybody could say that without even having looked at the exam, right? So it doesn't really signal to me that anybody's actually wrestled with anything or tried anything or got stuck on any particular thing. The biggest thing, the best thing you could do, the best thing anybody could do, I mean, Josephine or anybody else, is if like someone came in Monday and said, okay, I've been working with problem 2 and I got to part C, and in part C, I was confused whether I should use a negative sign or a positive sign, or like I didn't know whether to use velocity or acceleration, or say, the more questions like that, the more I can just say like, oh, yes, that's great. Well, in problem 2B, you have to use a negative sign because da-da-da. And I can answer a lot more questions like that and cover a lot more of the exam. And it's a lot more of a strong, it's just a much more constructive use of everybody's time. So the more that people can actually try things in advance and make their questions super specific, the better. On Monday and or Wednesday. Right. Oh, hello. Good to see you. But no, I'm glad Josephine's asking about this. That's all true. The more specific the questions, the better. And yeah, that's okay. And again, I'll just repeat. I know I just said it, but they are important questions. Right. Anything we give you answers to, and it's not like we're going to play hide the ball. Anything we do solve or release or something, and then you can assume we're going to you like use that to study and apply and learn the concepts, and then we'll tweak the question slightly on the real thing. But anything we don't give you an answer to in advance, then the trade-off there is you can assume, okay, well, we're going to get this exact question, so let's figure it out now together or whatever. Okay. All right. So now we're going to start dealing with homework 7. Let me just switch my screen or switch. Yeah. Homework 7, I'm going to skip. What just happened? Sorry. Something just happened to me. I'm going to go straight. Well, oh, I know what I was about to say. I'm sorry before that question. Everything in homework 7 now, I mean, not everything, the bulk of homework 7, well, it gets us into vectors for sure. And it gets us really into the details of vectors that got introduced in lab 3 and lab 4. But what you'll ultimately see is we do enough with vectors to start really applying Galileo's principle form number 4, like that VAC equals VAB plus VBC business that people wanted to see more application of. That's really going to happen here in homework 7. And it happens alongside of the thing we now introduced to deal with two-dimensional motion. The whole principle of vectors is this principle that every two-dimensional problem is really two one-dimensional problems happening independently yet simultaneously. And the way we put that into action mathematically is by viewing every two-dimensional quantity, taking every two-dimensional quantity and breaking it up into two one-dimensional components. A part of it, the quantity that lies along the x-axis and a part of it that lies along the y-axis. And we do physics on those two pieces independently. The way we break up all quantities into two pieces is we use our knowledge of right triangles, of SOHCAHTOA and the Pythagorean theorem, which can be regarded together in one statement, the statement on the board right now: sine squared theta plus cosine squared theta equals 1. You know, that trig identity that you all know. What that is, if you really think about it, that is a way of saying the Pythagorean theorem, but expressing it in terms of sines and cosines all in one statement. That is really a way of reminding you Pythagorean theorem and SOHCAHTOA now like live in a big way in our lives whenever we try to break down any two-dimensional quantity into two simultaneous yet independent one-dimensional quantities. So that's what we're going to do. That's what we're going to do right now. Sorry, my screen is doing weird things. I'm going to go to the homework 7. I'm going to skip directly. To where I think it starts getting thought-provoking and relevant to class. I'm going to skip directly to problem 1, part B. And first it asks me to draw, and this is very much like lab 3. All right, so it's asking me to draw. So pardon me for a second. I've got two screens going in a weird way here. Okay. We've got a gas station, which is like the origin of a coordinate system. Oh yeah, and the gas station is, yeah, like I say, it's like the origin of a coordinate system. It's on the x-axis. So we've got this line that the problem asks us to sort of instructs us how to set up a diagram. It's saying, let's label an x-axis an east-west line, and I'm going to choose right from the get-go to call east positive. I could choose whatever I want, but I've got to make a choice. I'm putting the gas station in the middle of this x-axis. I'm also going to assume, I don't know why it doesn't say, but I'm going to, well, oh no, okay. So now I'm going to put a Toyota. Sorry. Oh yeah, okay. So we've got a Toyota like 60 miles. Okay. Right, we've got a Toyota basically here. That angle is kind of bigger than it should be, but I'm estimating that's about 20 degrees southeast. We'll talk about that in a second. And it's 60 miles. Right, tell me if your diagram, if your diagram is substantively different from this, let me know. And then we've got a Pontiac. The Pontiac is, oh, I knew I was going to do that. I did not give myself room. Darn it. Sorry. Okay. Sorry. All right. Oh, sorry. Okay, and then the Pontiac is okay. Yeah, I know someone's here. I'll get them in 1 second. All right. Someone's here. I know. Okay. Okay. Yes, I think I've done this. Okay. All right. This is not a great diagram, but this is the situation. Now it's an estimated diagram. I mean, it's not drawn to scale. That has advantages. It's a sketch, right? And if your sketch is wildly different from mine, let me know. As you see, I am definitely estimating. Wait, there's something in the chat. I'm sorry. Oh, hello. Okay, no, got it. Okay. One quick thing to say about the diagram. I mean, I'm just following the instructions, right? And I hope you see that the instructions I'm following are very reminiscent of the kinds of instructions you were given in lab 3. What in effect is happening here, let's start with this, is these are, so this is class, no, I'm not, this doesn't say this in the homework, but these are displacement vectors. We've been dealing since the beginning of the course with displacement as a vector quantity, right? Meaning that displacement has magnitude and direction. But now we've expanded that idea and we're applying it to two-dimensional space or to higher dimensional space. So now the ultimate point is that direction here takes on a more elaborate meaning. Direction is no longer just a matter of positive or negative. It's a matter of an angle, right? What physicists say, now that we're in 2 dimensions of space, we have in effect 2 degrees of freedom, 2 axes. We have one choice at any given moment as to whether to go up or down, or north or south, or forward or backwards, or whatever. But then we also have this other choice as to whether to go left or right, or east or west, or whatever you want to say. So we, from here on in, are expressing our vector quantities with arrows. So let me take a quick, so from now on, a vector is an arrow that is used to represent a vector quantity. And when I say that an arrow is used to represent a vector quantity, I mean it in a very precise, specific way. From here on in, the length of an arrow represents the magnitude of the vector quantity. And that means assuming some scaling factor, like say the magnitude of the vector quantity is 3 meters, then you would draw an arrow in principle that was, say, 3 inches long. Or you could choose a different scaling quantity, like 1 centimeter per every meter. But whatever scaling factor you're tacitly choosing, you stay consistent with. So the length of an arrow represents the magnitude of the vector, and the tip-tail orientation of the vector represents the direction of the vector quantity. direction from now on in 2 dimensions, direction means some kind of angle with points of the compass. Right. So I'm just like laying this out. I mean, I think you guys saw this in lab 3, and I think it's most of it's sort of self-evident, but like from now on, we say something like 30 degrees northeast or 30 degrees northwest, and those are 2 different angles, right? And to be super clear, one thing that's not always clear to people, to say, okay, so sorry, for example, to say 30 degrees northeast means, here's the part that's not totally obvious always. If we say 30 degrees northeast, we mean 30 degrees north of east. Whenever someone says northeast, there's really a secret word of in there. Or if they say southwest, they mean south of west. So 30 degrees northeast, just to be explicit for all time, means you picture some dotted line that's pointing to the east, right? And then the vector that you're thinking of would be raised 30 degrees, I'm assuming that to the right is east, assuming to the left is north, assuming that you've already decided that up is north. Sorry, if east is right on your page, west is left on your page, north is up on your page, and south is down on your page, which is a decision. Then to say 30 degrees northeast really means that you draw an arrow that forms a 30-degree angle in the northerly direction compared to east, right? Again, by the way, this is kind of like how we say VAB means velocity of A relative to B, right? Like the order matters, in other words. It's similar to that. If you say 30 degrees northeast, what you literally mean is 30 degrees north of east, which technically means sidebar, 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 sidebar. Technically, that means that the angle 30 degrees east north is a different angle. Right? I mean, it's not one that people say in English very often, but you do hear it in physics. Like to make an angle of 30 degrees east-north would mean that you picture a line going up and then you place an arrow 30 degrees to the east of that, just saying. Okay, so the language is actually literal. All right, anyway. So, okay, so back to the problem. So, I'm going to say one more thing about vectors, though. Okay, I'm using this problem as an excuse to lay vector concepts out on the table. From here on in, again, a vector is an arrow that's drawn to represent a vector quantity. The magnitude of the vector quantity is represented by the length of the arrow. The direction of the vector quantity is represented by the tip-tail orientation of the arrow, okay? The assumption is that we're drawing these arrows as best to scale as possible. Like I made a sketch. It's not a very good sketch, but what I'm trying to do in this sketch is, you notice in my sketch, which I'll turn back to in a second, like one of the arrows was supposed to have a magnitude of 60, the other was supposed to have a magnitude of 30. So I'm trying to make the first arrow like twice as long as the other one. Like that's what you try to do. The reason that you try to be somewhat precise about it is I want to make a claim about these arrows before I go on. Whatever the vector arrows represent, okay. Okay, so the thing I'm saying is, first of all, let's get straight. The whole idea of vectors, why they're so powerful, is we use them to represent any kind of vector quantity. So an arrow could be used to represent a displacement. That's what we're about to do in this problem. or an arrow could be used to represent a velocity, or an arrow could be used to represent an acceleration or a force or a field or whatever. Any quantity that has magnitude and direction in physics can be represented with this arrow. So the arrows can mean all kinds of different things, but a bunch of rules apply to these arrows regardless of what the arrows are, regardless of what physical quantity the arrows are representing. And the rules are these. So whatever the arrows represent, the following rules apply. One, only the size and orientation of the arrow convey information. This is a subtle, strange, but important point. And again, I will get back to the problem in a minute, but I want to make it clear. Like I know it's obvious. I mean, I know you've dealt with it before. It's an arrow. It represents a vector quantity. Okay, so the size of the arrow represents the magnitude of the vector quantity. The way the arrow's facing represents the direction of the vector quantity. Like it almost seems obvious, right? Like, okay, so we're using arrows. I mean, we could have thought of that on our own. But here's the first subtle power of these arrows is that only the size of the arrow and the orientation of the arrow mean anything. Only the size carries information, tells us something about the vector quantity, and the orientation conveys information about the vector quantity. What that means is the fact that only those two features of the arrow mean anything. What that means is, so okay, I'll call that A if you want. What that means is, therefore, nothing else about the arrow means anything. Specifically, where the arrow is drawn on our page does not mean anything. Does not mean anything. Or does not convey any information. Okay, and that's like super important. I mean, it took me years and years to realize this. Where you draw the arrow on the page doesn't convey anything about the vector quantity. Therefore, and this is such a Galileo type point, therefore, we can and must make choices about where to draw the arrow. What do I mean by that? I'm saying that a vector, the power of a vector, the secret power of vector, that honestly, I never understood until I did. The secret power of why vectors do anything for us is that it doesn't matter if you draw a vector in the top left corner of your piece of paper or the bottom right corner, it's still representing the exact same thing. Therefore, you can draw it wherever you want on the paper. You could draw arrows wherever you want on the paper and they still mean the same thing. Therefore, if we make very deliberate choices about where to draw the arrow on the piece of paper, then they become powerful tools. What the heck do I mean by that? I'm going to say, and then we will go on. So therefore, rule 2, when two arrows are placed tip to tail, You may know this. You may have said this explicitly. You may have seen, well, it doesn't matter. Right? When two arrows are placed together, tip to tail, then the arrows represent addition of vector quantities. To A. The sum of two vector quantities, the sum of two vectors, is an arrow from the original tail to the final tip. This is the key thing to the whole thing. And I'm going to draw one example. We're going to go back to the Pontiac right now. But I just want to lay this out. What I'm saying is the real power of vectors, and remember, the real power of these arrows is that they can be used as calculation tools, whether we're talking about displacements, velocities, accelerations, forces, fields, whatever. If we draw these arrows somewhat to scale, as you in effect saw on lab 3, if you draw these arrows in effect to scale, then I'm just drawing this one. I'm drawing this and then we'll go back to the problem. Example, if you draw two arrows in effect to scale, and you, since you're allowed to place them anywhere you want on the piece of paper and they still mean the same thing, if you place two arrows together tip to tail, like you place the tail of one on the tip of the other, then what you've done is add those two vectors together. And the answer to that addition problem, here, let me make this more vivid, sorry. Let's make this really, these two vectors really different. Okay, say these are two vectors, A and B. They're placed tip to tail. The sum of these two vectors would be represented by a third vector that goes from the original tail of one to the final tip of the other. And what we're saying is that C that completes the triangle, that vector C is the sum of vectors A and B. Again, specifically, and I'll go back to the Pontiac and Toyota in a second, but like the whole purpose of lab 3 that you did weeks and weeks ago is that when it comes to displacements, you can really, it almost seems so obvious to some of us that it almost doesn't seem worth saying. Like when you're talking about displacements, you know that if you started at this point and you walked the way that vector A is telling you, you walked that far and in that direction, and then you stopped, and then you walked in the direction that point B is telling you, and for the length of distance that vector B is telling you, where you'd end up at the end of the day. The sum of your two displacements, where you'd end up at the end of the day, could be represented by an arrow that went from your original position to your final position, right? Like, it's sort of evident if you're just thinking about walking, that that if you want to add two vectors, if you want to accumulate the effects of two vectors, you place them in sequence, tip to tail. Well, we're saying, so if you sort of get that, or you sort of saw that in lab 3, what we're now saying is hold on to that concept and take it really seriously, because we're saying from here on in that we're going to do that with all vectors of any kind. We're going to assume that when we place them tip to tail, we're adding them, and similarly then all the rules of addition apply, like vector C must, then therefore vector C minus vector B must equal vector A, and vector C minus vector A must equal vector B. right? If placing two arrows tip to tail means adding them, well, then similarly, placing them tail to tail must mean subtracting them, or tip to tip must mean subtracting them, right? So in the end of the day, the real purpose of vectors, if you sort of draw them to scale, is realizing that the more physics problems, once you can break down and translate a physics problem into pieces that involve addition and subtraction, you then move vectors around the page and put them together in various shapes to perform addition and subtraction. Fine. Like, so the way we're going to do all this VAB plus VBC equals VAC business that people are asking for more examples of, the way we're going to add these kind of complicated vector velocity quantities together is we're going to draw arrows and put the arrows together. Okay, so the key to these vector arrows really is understanding that placing them tip to tail means adding them. Okay, so I've already said, so that's like the theory of it. All right, so now let me go back to the Pontiac and let me go back to the Pontiac and Toyota and answer whatever he's asking there. Sorry, just switching my screen. And that was a little bit of a dive. All right, so we got okay. So I'm going back to homework 7, question 1B. So I've drawn my angles and I've drawn my vectors. So now it asks, it says how far and what direction, how far and in what direction is the Toyota from the Pontiac. Oh yeah, okay. Well, if the Pontiac is 30 miles northeast, 30 degrees from the Toyota, this is like relativity now. If the Pontiac, it's symmetric. So I'm going to say, I mean, if told us that the Pontiac is 30 degrees northeast from the Toyota, then the Toyota is 30 miles at 30 degrees southwest of the Pontiac. I'm just flipping, it's mirror image, right? I mean, it's hard for me to go back and forth between, I'm not looking at my diagram now because it's on the other page, but if I'm reading the problem, if the Pontiac is northeast of the Toyota, then the Toyota is southwest of the Pontiac. It's the exact opposite. What I'm really doing is imposing a negative sign. I'm really putting a negative sign, flipping the values, but I'm flipping east and making it west. Sorry, I'm flipping east and making it west, and independently but simultaneously, I'm flipping north and making it south. So just note, I guess what really this is trying to point out is note each axis has its own plus or minus sign assignment. They're independent, right? In other words, it's no longer, well, okay, I think you get the point. It's no longer good enough in 2 dimensions to say -50 or something. That doesn't mean anything. The negative sign could be applying to the x-axis, or the negative sign could be applying to the y-axis. So this is why we need angles now, because each axis has its own plus and minus. Okay, anyway, and then question 3, I'm dragging this out way too much. Question 3, it says, how far and in what direction is the gas station from the Toyota? Well, what we know, we know that the Toyota is 60 miles, 20 degrees southeast from the gas station. Thus, the gas station is 60 miles at 20 degrees north west from the Toyota. And did I read the last one? Yeah. Okay. And then it says draw an arrow from the gas station to the Pontiac. Okay, I have to go back to that. Okay, and here's where I'm a little insecure that my diagram, I'm a little insecure about my diagram, but I have a feeling, well, yeah, I have a feeling that this should be shorter. Okay, so it says draw, it says draw an arrow from the gas station to the Pontiac, and this is so something like this. And what we're getting at is, okay, here we go. This is what time is it? Okay. This he's sort of walking you through step by step, but what we're really getting at is that red vector that I just drew from gas station to Pontiac. If I figure out the length and the direction of that red arrow, then I would have figured out the sum of the two vectors GT and TP. In other words, if someone ever were to walk directly from the gas station to the Pontiac, right, they are doing the equivalent of, they are covering the same displacement. They're ending up at the same place as if someone had walked from the gas station to the Toyota and then from the Toyota to the Pontiac. So what we're so if we could find out how long this red arrow is, we are finding out the sum of the two black arrows. And here's the thing now. Okay, well, so I'm going to do that, right? I mean, that's the point of the whole problem. The whole point is to add to, this is a problem in addition of displacement vectors. Sorry. And that's what we're going to do right now. And it's going to take us a little while. This is question 4. Sorry. We are trying to add the two displacement vectors together to get a final displacement vector. Let me make a couple of things explicit about that. Our final answer is going to be a vector, right? So our final answer has to have magnitude and direction. Like, we're not done with the problem until we get a number that represents some kind of distance and an angle that represents a direction. That's number 1. Number 2, if our vectors were drawn perfectly to scale, we could obtain the answer so to speak, graphically by direct measurement. I'm just saying this is important. Like, the power of these vector arrows is if you take them seriously, right? If you take them seriously and you draw them actually to scale, which of course I did not, but if you draw them to scale, and again, this is the point of Lab 3, if we drew these two arrows to scale, then the answer we're looking for could be obtained by just literally measuring the red line that completes that triangle. Like if we measured its length with a ruler, and if we measured the angle that it was forming with a protractor, then that answer would be the answer we're looking for, the sum of those two vectors. That may not seem very interesting, except it does become interesting once these vectors represent more complicated quantities like velocities or something. Like we could get the answer to addition problems by just measuring shapes on a piece of paper. The vectors do computational work for us physically if we treat them physically with precision. But we generally don't do that. That's what Lab 3 was. That generally takes a lot of time and a lot of care and is very experimental and requires tools and everything. So what we do instead, what I'm about to do right now with our remaining time, is or we can add vectors, and this is what we're going to do right now. We can add vectors analytically, and that means, by a method that does not require precise measurement, or we can add vectors analytically, thus using our diagrams just as a rough sketch, as an approximate guide. We can add vectors analytically by a method called component method. And the component method that I'm about to do right now, that I'm overbuilding, the component method that we're going to use for all vectors, like we're going to see it right here with displacement vectors, but we're going to believe that it works for velocity vectors, for acceleration vectors, et cetera, et cetera. The component method is the mathematical way of using Galileo's principle of breaking up a two-dimensional problem into two one-dimensional problems. We're going to break up 2D into two independent but simultaneous 1D problems by using trigonometry. Okay, so here we go. So here's the method. Okay, I'm going to draw the diagram again because I'm going to blow up the diagram. Well, I'm going to zoom in on the diagram. Here's the method. So here's the method. First, we zoom in on each vector individually. Okay, so what I mean by that, like I'm adding two vectors, right? This is a method for adding two vectors. The two vectors are the vector from the gas station to the Pontiac, from the gas station to the Toyota, and the other vector is the vector from the Toyota to the Pontiac. I'm trying to add them together, right? So what I'm going to do first is I'm going to zoom in on each one individually. So I'm going to look at that vector, that displacement vector that's going from the gas station to the Toyota. So that vector looked like this. call it vector T, and it equals 60. Right? It's 20 degrees south of east, and it's 60 miles long. That's the vector, right? So I'm zooming in on it. The next step I'm going to do, so I'm zooming in on that one vector. I'm zooming in so I can first and foremost break that vector into components. I'm going see that vector is a two-dimensional thing. Someone's saying that like the Toyota is 60 miles away from the gas station, but in a two-dimensional way, in a southeastern way. I want to view that as two one-dimensional displacements that are occurring simultaneously yet independently. In other words, I want to do what you did in lab 3. I want to say, well, you know what? Something that's 60 miles southeast from something else is really a certain number of miles south, while at the same time, it's a certain number of miles east from something. I want to know what those two numbers are. In other words, I'm saying this. I'm going to break this up. I'm going to say southeast is really some amount east plus some amount south. Southeast is really some amount east plus some amount south. And when I say plus, I mean it literally. Like, remember, when you draw vectors tip to tail, you add them. And conversely, when you want to add vectors, you place them tip to tail. So I'm saying if I walked 60 miles, again, this is all the lab 3 thing. If I wanted to walk 60 miles southeast, what I could have done equivalently is walked a certain amount east and then walked a certain amount south, and I would end up at the same place, right? So 60 southeast is really equals some amount east plus tip to tail, some amount south. And look at where my tips and tails are, right? Like I'm saying southeast is the sum of some east with some south. And why do I keep saying it backwards like that? Because if you notice, southeast means draw an angle south of the eastern axis. So when you want to think of it in a tip to tail way, if you draw the eastern axis first and then go south from it, like that's what we're doing when we go southeast, right? So I always think of southeast as some amount east plus some amount south. Secretly, what I'm saying is I always draw the horizontal first. If you get used to that, it makes everything a lot easier. So, okay. So now I believe I have a triangle here. I'm treating this individual vector as its own right triangle. Hint also to those people who did practice this or got somewhere far, but then got into trouble later on. I'm saying, notice I'm not looking for I'm not up to yet the triangle between the two vectors. I'm zooming in on each vector one at a time and turning it into its own right triangle. I'm just going to say that again, because this is what people like. I'm not making triangles out of a ton of vectors together, or at least not at the beginning. I'm saying every single vector in the world is the hypotenuse of its own little right triangle, because we're viewing any random direction you could ever go as secretly the simultaneous yet independent sum of some amount that you could go horizontally or like east-west with some amount that you could go vertically or north-south or whatever. And necessarily, we're breaking up a vector into two independent coordinate axes that are perpendicular with each other always. Like the x-axis is perpendicular with the y-axis. So every vector has its own little right angle built into it. And I'm going to use my knowledge of right triangles. I'm going to say, well, you know what? Well, here, I'm just going to draw it again over here. So I've got this thing, right? This is 60 miles. This is like the vector t, call it. And so the magnitude of that vector is 60. And I'm asking myself, how far east did I go and how far south did I go equivalently if I went 60 miles southeast? And the answer comes from SOHCAHTOA, right? I mean, everybody knows. So in math, in math classes, you usually use SOHCAHTOA to, you usually, like, it's a way of saying if you know the sides of a right triangle, you can get the angles or the sines and cosines of the angles. We go the other way around generally in physics. We say, oh, because of SOHCAHTOA, like I know, for example, that the cosine of that angle 20 equals the adjacent over the hypotenuse, right? I know that from SOHCAHTOA. So the significance of that is I multiply both sides by hypotenuse. I say that the adjacent, therefore, is hypotenuse times 20 times cosine of 20. And it's the sides really that I'm looking for. Like, what is the hypotenuse is already known to be 60. And the adjacent is what I'm looking for up here. I'll call it T sub X, the X component of this vector T, this vector that goes from gas station to Toyota. So I would say TX, the length of TX is 60 cosine 20, right? And which is a number I can get on my calculator. But similarly, I could cut straight to the chase and say, okay, TY is 60 sine of 20, and those are just numbers. If my calculator for this kind of context, my calculator would be in degree mode. So, cosine 20 is just a number and multiply it by 60. So TX equals approximately 56.4 miles. Are these all in miles? I think they're all in miles. And TY approximately equals 20.5 miles. Now notice, so what we're saying, we're saying that to walk 60 miles in this particular direction is equivalent to having walked like approximately 56.4 miles east and then walking approximately 20.5 miles to the south. And I'm just storing that information for a moment. Okay, I'm saying they're equivalent. Or put another way, I'm saying in a vector sense, 56.4 miles to the east plus 20.5 miles to the south in a vector sense equals 60 miles to 20 degrees southeast. Now, again, no, we're adding vectors here. I'm not saying that the number 56 plus 20, I'm not saying that that equals 60. 56 plus 20 equals like 76. That's if I treat those numbers like distances. If I just add a distance of 56 to a distance of 20.5, then I would get something like 70. But if I add them as displacements, if I take into account direction, what we're saying is if you walk 56 this way and then you walk 20 that way, your overall displacement is exactly this much. I don't know if that makes sense, but that's now why am I saying that? I know I only have 17 minutes. It doesn't seem like I've answered anything. I haven't yet answered anything. Why would I do this? I do this every time for the component method. I take every single vector that's involved, that's being added, and I break it up into its individual independent X and Y parts. So I'm now going to do it to the other vector. Now the other vector, and you always do this. So the other vector was, the other vector was 30, it's like shorter, 30 miles. And this is the Pontiac now, so we'll call it vector P. The 30 miles at 30 degrees northeast. So I'm zooming in on this now. Now zoom in and break up. So I'm going to do the exact same thing, but I'm going to cut to the chase now because it's like always the same method. Like this is definitely a right angle. Every vector is the hypotenuse of its own individual right triangle. So I want to get its components now. I want to get px and I want to get py. So I cut to the chase and do the same thing. I say px will be p times cosine of the angle. In other words, 30 times cosine of 30. And cosine of 30 is like 0.87. So 0.87 times 30 is like, it's like a 24.3 or something like that. Or I mean, 20, whatever. Okay, 20, yeah. So like approximately 26.0. And py will be 30 sine 30. The sine of 30 is 1/2. So that's exactly 15. So what we're saying is this triangle, the P triangle, looks like this. Py equals 15, px equals whatever I just said, 26. Okay. So I did the same procedure on both. And notice, get used to the fact. I mean, I don't know if you've ever, the whole thing about SOHCAHTOA, and this is all about SOHCAHTOA and Pythagorean theorem, because it's all about right triangles. If you start, a hint to the wise, a word to the wise, if you start doing some trigonometry or something on some kind of triangle, and this happens to people, if you start drawing things and then you're dealing with a triangle and you're like, oh, but wait, this triangle is not a right triangle, so I need something other fancy thing like law of cosines or something like that, then something's wrong. Everything is a right triangle. This whole methodology is about reducing the world to two perpendicular worlds. So every step we do involves a right angle somewhere. Now, why did we do that? We're not done, but we're almost done. We certainly will be done in time. Why did we do this? Why did we zoom in on each vector individually? Because we're separating the whole problem into two one-dimensional problems. Again, it's what you were doing in lab 3, whether you like thought about it this way or not. Now, so in other words, now we can add independently but simultaneously we've now broken the two-dimensional quantities into pairs of one-dimensional quantities, and we're just going to track the one-dimensional quantities. What I always do is I make an XY chart. I go like this. Like I'm literally dividing the universe, the world, into an X world and a Y world. The whole premise of this is physics happens in the X world and physics happens in the Y world, and the two happen independently. Again, like lab 3. So what do I mean? I mean like the Pontiac, I'm sorry, the Toyota is being added to the Pontiac. Those two displacements are being added independently along the x-axis and the y-axis. So the Toyota, right? The Toyota here, yeah, here's my Toyota triangle. The Toyota brought me 56.4 meters along the x-axis, right? And then it brought me 20, and it brought me 20 independently. It brought me 20.5 miles along the y-axis, but now I have to be careful. Look at my triangle. Notice also, please notice that that every side, I'm not just drawing triangles. It's not just a math class. It's not just a geometry exercise. Everything I'm drawing, every side of every triangle I'm drawing is an arrow with a tip and a tail. The whole purpose of this is to be tracking directions. right? And so I highly encourage, I demand that you do that too. I'm not just drawing raw triangles. I'm putting together arrows. So I look at this original triangle, the Toyota triangle, the horizontal displacement of the Toyota was 56 to the right, to the east, which we previously designated as positive, right? But the vertical display, the north-south displacement was 20.5 miles to the south, which I believe in our original coordinate system we designated as negative. So I got to take that seriously. I'm going to put a negative sign there. Okay, I'm looking at my arrows and taking them seriously. Pluses and minus signs each apply independently to each axis. Okay, so and now I go to the Pontiac. The Pontiac brought me to the right 26.0 miles, and it brought me up or to the north 15 miles. So I don't put any negative signs there, right? So notice I'm adding the two vectors because that's what the problem's asking. The problem's asking to find the exact distance, direction, angle from the gas station to the Pontiac. I'm looking for the total displacement, the sum of these two displacements. So I'm adding the two displacements together. I'm adding them individually on their own axes, but I'm adding them. However, that doesn't mean that there couldn't be minus signs involved, right? I'm not, okay, I think you understand it. So now I'm literally going to add, I'm accumulating the X. So I add up the X's and I get like 82.4 in the X direction, and I add up the Y's. And so I get negative 5.5 in the Y's, right? And what are we really saying physically? We're saying that like one thing took you that way and then that way. The other thing took you, that way and then that way. So in effect, so what we're saying is the X quantities can't communicate with or interact with the Y quantities. They interact only with the other X quantities, just like lab 3. Like if you had two directions in lab 3 and you broke them and you noticed that one somehow took you 3 miles east or 3 yards east, and the other direction, as complicated it was, somehow took you 3 yards to the west, you realized in lab 3 that 3 yards west and 3 yards east cancel each other out and bring you nowhere on that axis, even while other things could be happening on the other axis. Like that's what we're saying here. Okay, so now I'm almost done. I mean, and class is almost done, but I don't have an answer yet. What I'm looking at right now says my final displacement, my total displacement, which is to say from gas station to Pontiac, from gas station to Pontiac, apparently brought me 82.4 miles to the east, while bringing me 5.5 miles to the south, right? And how do I know south? Because of that negative sign, right? So what does that mean? It means my final answer is one final right triangle. I literally draw these out. Now I go, okay, and I always draw the horizontal first. So, and I try to draw sort of the scale. So I go, okay, approximately 82 point. This is my final displacement. So we'll call this G, I guess. GX goes, well, no, okay, we'll call it TP, I guess, or PT. TPX goes, whatever that number was, 82.4 to the east, but while also bringing me independently, but simultaneously bringing me 5.5. So I'm trying to do it sort of to scale. TPY was approximately 5.5 to the south. So my overall displacement, my overall answer that I'm looking for is this arrow. And this arrow, if my original diagram were drawn to scale, my original pages and pages ago, the original arrow that I'm looking for to complete that original triangle is this arrow right here that I've just redrawn in a different triangle. Like, and if everything were drawn perfectly to scale, both those arrows would literally be the same length and pointing in the same direction. What that length and direction is, I'm about to find out right now. Like, I'm looking for TP and I'm looking for the angle. Well, how do I get TP? TP, like the length of this thing, equals, it comes from Pythagorean theorem. It is the square root of 82.4 squared plus 5.5 squared, right? So that's not going to be an exact, I mean, I'm going to have to approximate that, but hold on one second. And we've got 5 minutes. So we literally do, and I should really get a calculator out for these things. Okay, so it's like 82.6, which really shows you that my diagram really is not to scale. I mean, you see my vertical line should be much, much shorter than it is compared to the horizontal line if I'm drawing this, because the hypotenuse is only slightly bigger than the horizontal component. And that means the angle I'm about to get is probably going to be a very, very small angle, much smaller than my picture depicts. How do I get the angle? So this is part of the answer, right? This is the magnitude of the answer. That's only part, but I'm also looking for direction. But the magnitude, in other words, the distance part of my answer is 82.6 miles. Now for the angle, what I say, I think there's your choices, but it's SOHCAHTOA. I think the easiest, most direct thing that I always do, since I know my vertical and horizontal component, I always go, okay, tan of the angle, tangent of theta, equals TPY over TP equals opposite over adjacent, right? So in other words, equals 5.5 over 82.4. That's the tangent of the angle equals that. Therefore, the angle equals the inverse tan, the arctan on your tangent going backwards, tangent to the -1 of 5.5 over 82.4. So that is, I mean 80, yeah. 5.5. Right, so it's a really tiny angle. It's like 3.82 degrees southeast. How do I know? Make that bigger. How do I know southeast? Because I'm looking at my picture and I'm looking at the arrows. What did I just say? 3.82 degrees southeast. So that's the direction. And it's like we've got 2 minutes left in class. That's my final answer. The magnet is a vector whose magnitude is a displacement vector, whose magnitude is 82.6 miles, and whose direction is 3.82 degrees southeast. Now, I've been looking at like 3 pictures at once while doing this, so I totally apologize if I missed the chat completely. If there is there anything in the chat? Wait. Oh, cool. I love a certain person in the direct chat always tells me when, okay, good. I don't know if you're really being polite or what, but thank you, person who just said that. It makes more sense. Okay, wait, we got 1 minute. So yeah, hopefully it does. Now, here's the big thing. I know that we only did just one problem right now. I'm aware of that. But that is how you do all these vector problems. Like the next problem on the sheet is the same type of problem, but with velocities. So it's like harder to conceptualize. It's like the next thing we have to talk about next time is like what this means for velocities. But the whole thing is you do the exact same procedure when you're adding velocity vectors together. And how do you know which velocity vectors to add together or what it means? That's the whole thing of VAC equals VAB plus VBC. Like, so adding velocity vectors together takes the Galileo principle and combines it with the trig functions of SOHCAHTOA and Pythagorean theorem. But this procedure is what we do to add two vectors of any kind together for life. Okay, so that's class. So, okay. Oh, no. Okay, no, cool. I really do appreciate it. Okay, so yeah, I'll be here if there are any questions. I'll post the thing tomorrow night, blah, blah, blah. Have a nice lunch. No, yes, and thank you very much, all of you. Oh, okay. Yes, thank you.
Have a great day, Professor.
You too. Have a great day. Thank you. Have a good one. Yes, have a good one. Thank you. Oh, thank you. That's very nice of you to say. Thank you. Okay, cool. I hope it helped. Oh, and do you have a question or? And should I, or do you have a question, Christina, or, but thank you for saying thank you. Do you have a question or should I? Okay.